Hello everyone. So today is the third day of the fifth week. So today we are going to start with to find out representation of any given molecule belonging to any particular point group without worrying about formation of a matrix. This will be necessary in the next part of this class, when we will be talking about forming symmetry adapted linear combination, or in the next part when we go to the case of spectroscopy. Because it's not always possible to form a huge matrix, and ultimately we are going to use the characters, okay, not the matrix. So if by some way, if we can evade forming a large matrix and directly can find out the character, that will be immensely helpful. Okay, so quickly I will give you an example how to do that. Okay, so let's start with a particular molecule, say for example N2F2, which has a trans configuration and it's a planar molecule. So without worrying about the lone pair of electrons, we will try to find out how we can find a representation in terms of character, not worrying about the matrices. So how to do that? So there is a concept which is also known as the concept of unshifted atom. So what does it tell you? That is, once you know the structure and know the point group and the corresponding symmetry operations in it, you apply the symmetry operations on this molecular structure. Now you can choose your basis function whatever you can. For example, I can choose all the s orbitals of say 1s of these two hydrogens and 2s of this two nitrogens, and that can act as my basis set having 4 basis functions. I can still have all the x, y, z coordinates of all the atoms in this molecule as my basis functions. So if I say consider all the x, y, z coordinates, so for x, y, z coordinate system I will have total 4 into 3, 12 basis functions in my set. Now earlier what we did, we tried to form a matrix which is 12 by 12 for each and every operation, okay, and from there we found out its character, and then we reduced it and whatever we did. So here what we are going to do, we are still trying taking this x, y, z coordinates of each atoms as my basis function. Now we are going to use this unshifted atom concept here. So what it tells is, when I operate all the symmetry operations, say for example what are the symmetry operations that I have? I have identity C2, I have inversion symmetry, and I have sigma H. So these are the 4 symmetry operations that are possible for here. So for example, if I operate C2, which is here on this molecule, whichever atoms are shifting from its position will contribute nothing to the diagonal of the matrix that I can form. So for us, when we are dealing with characters, it's the diagonal element which matters. Off diagonal element doesn't contribute anything, correct, to the overall character. So once the atom, say if I mark this one like 1, 2, 3 and 4, upon a symmetry operation, if one is shifted to some other atom, then this will not contribute anything to the overall character. Now if my basis function is such that, so here it is like x, y, z, so on this atom I have 3 basis functions, right? So I have x, y and z. So the same thing will be applicable to these basis functions as well. So that means all 3 basis functions, x, suppose this x1, y1 and z1, each one of them will contribute 0 to the overall character. In case the atom is not shifted, the atom remains there, then this any basis function on that atom that we are taking will contribute 1 to the diagonal, right. So, for example, for any operation, take an example of identity. So, if I operate identity on this one, and let us concentrate only on this hydrogen atom. So, this one will remain unchanged, unshifted, right. So, this atom and any basis functions on that atom will contribute 1 each to the overall character. So, x1, y1 and z1, they will contribute 1 each. So, from this hydrogen atom I will get a contribution of 3 to the overall character, because x1 is giving 1, y1 is giving 1 and z1 is giving 1. Suppose I would have an the 1s orbital as my basis function here instead of this x, y, z, then that would contribute or a character of 1 to the overall character of the representation. So, now let us start with all the symmetry operations so that it becomes more clear, right. So, we will start with the identity operation and we will directly go to the representation, right. So, this molecule has point group C2H, we have seen that earlier, and let me write down all the operations here. So, and let me call my representation as gamma, all right. So, identity operation will not shift any one of them, correct. So, each one of them will contribute to the diagonal. Now, each of the atom contains 3 axes which we are using as basis functions. So, each atom will contribute 3 to the overall character. So, 3, 3, 3 and 3. So, total 12 will be contributed to the diagonal. Now, you remember when we formed the matrix for identity element, we had an unit matrix of order that is given by the number of basis function in the basis set that you choose. So, here also we are getting the same result. So, overall the character should be 12. So, see, I do not have to form the matrix. Now, E is very easy, but let us see what are the other symmetry operations that we have. So, for example, C2 is in this direction. So, if I operate C2, 1 will go to the place of 4, 4 will go to the place of 1 and 2 and 3 also will interchange. So, none of the atoms are remaining in their place. That means, none of the basis function will contribute any positive value to the overall character, meaning the total character of the presentation corresponding to C2 operation will be 0. Okay. Now, let us look at I. So, what does I do? So, I does this pretty much same thing as C2 does. So, 1 and 4 gets interchanged, 2 and 3 gets interchanged. So, there is no unshifted atom, meaning every basis function will contribute 0 to the diagonal, leading to an overall character of the presentation to be 0. Now, what about sigma h? So, sigma h will be in this plane. So, what it will do? It will keep all the atoms in their place. Now, here we have to worry about something. We are considering x, y and z axis, right. So, if this direction is z axis, then the molecule is in xy plane. So, sigma h will not do anything to x and y will remain as it is. So, overall each atom will contribute 1 for x and 1 for y. So, altogether I have 2 into 4, 8 being contributed by the x and y coordinates of all the atoms, correct. So, I have plus 8 contribution. Now, what about the contribution of z? So, when I reflect on this plane, plus z will become minus z, correct. So, each one of this z coordinates will contribute 1 to the diagonal, but with a negative sign, right. So, 4 z coordinates z1, z2, z3, z4 will contribute -4 to the diagonal. So, overall the character will be +4. So, this is what I get. So, see how easily I can find out the representation of a molecule in terms of their character without worrying about the matrix representation. Okay. So, once you find out the representation of any given point group, you can do whatever you want in the next step. Say for example, if I want to know about say the vibrational modes. Okay. So, what I have to do, I have to next see if it is reducible or irreducible, and by now you know that this representation is clearly reducible because the square of the characters, okay, sum of the square of the characters of this representation is higher than the order of the group. So, this is reducible. So, you can reduce it by using the formula that we have already talked about in the last couple of classes. So, you can find out how many irreducible, how many times one irreducible representation occur in this particular representation, right. So, there will be 4 irreducible representation for this one, that also we have seen earlier for C to H point group. So, say A1G, A2G, B1G, B2G. So, how many times A1G will occur, how many times A2G will occur, how many times B1G or B1U will occur. So, that you can find out, and from there you can go on and solve the problem that you are trying to solve. So, with this we are pretty much in a position to deal with the actual applications of this symmetry properties of a molecule, and we are going to look at one of these which is known as symmetry adapted linear combination. But in order to be able to deal with this kind of linear combination of atomic orbital, which is very vital to find out which atomic orbital will contribute to the formation of certain MOs or hybrid orbitals, we need to know about the relation between group theory and quantum mechanics. The reason is all these orbitals that we will be talking about, they are characterized by their wave functions. So, we need to know about these wave functions and how these wave functions, their properties are related to the symmetry properties of that particular molecular structure. So, in the next step we will look at that. So, for this we do not need to have a very detailed idea of quantum mechanics, but if you have some basic knowledge about wave equation and a little bit of quantum mechanics, that will be very much helpful. So, for any given physical system, the wave equation is given by this relation. Okay, this is the Schrodinger equation, where we do not talk about any time. So, psi is a wave function which defines the state of a system, and H is the Hamiltonian operator. This is an energy operator, right? So, when H operates on this wave function psi, it gives a value which is a constant value, which is the energy, or given as E. So, this wave equation says that the function is an eigenfunction, and the result of performing the operations, which is Hamiltonian here, will produce the function itself, and which will be multiplied by a constant, which is also known as an eigenvalue. So, whoever of you have gone through the basic quantum mechanics, you know that this eigenfunction and eigenvalue equation, and here exactly by this Schrodinger equation we are finding that psi is an eigenfunction of this Hamiltonian operator for the system, and E is the energy eigenvalue. So, and normally this is how it is represented. Okay. Now, there are certain properties of this eigenfunctions and this operators and the eigenvalues. So, suppose I am considering one particular molecule. So, a molecule will be composed of certain atoms. So, these atoms, if I consider them as particles, so what a symmetry operation does, it interchange some of these particles, okay, so rearrange them to give an indistinguishable structure. So, for a system where two or more particles are interchanged by carrying out a symmetry operation on the system, the Hamiltonian remains unchanged, which is quite easily understood, because a symmetry operation, it doesn't make any change in the molecule, it merely reorients, I mean it interchanges certain atoms, certain bonds, and ultimately it gets an indistinguishable structure. So, two indistinguishable structures cannot have two different energies. So, Hamiltonian operator, which gives us the energy when it is operated on the eigenfunction of the system, this Hamiltonian is unperturbed by any symmetry operation. Therefore, symmetry operation, if I write symmetry operation by the term R and Hamiltonian as it is by H, then H and R, they also commute, right, because symmetry operation doesn't do anything. So, here that expression is written here, that is RH equals to HR, because they do not interfere into each other's work. Operating Hamiltonian on the molecule, molecular wave function is not going to do anything to the symmetry properties of the molecule, and vice versa. All right. Now, the Hamiltonian operator, apart from being showing commutative property with the symmetry operations, it also commutes with any constant factor, right. So, for example, here it is shown like wave function is given as psi, but if I multiply this psi by any constant, then that also doesn't change the state of the system, only the normalization constant condition just changes. So, what is said here is that the Hamiltonian, it also commutes with that constant. So, therefore, I can write that if I have a constant c multiplied to the wave function psi, which is an eigenfunction of the Hamiltonian operator, then c and h, they commute. Okay. So, this is an important thing that we should note. Another important property of these eigenfunctions are these eigenfunctions are orthonormal. Okay. So, what do you understand by orthonormal? Means that two eigenfunctions, say psi I and psi j, they are orthogonal to each other, and each of them are normalized. Okay. So, if I mathematically want to show that, that is shown here. Okay. So, if I take psi I and psi j and then integrate over all the coordinates given by this tau, then this integral will survive and give a value of 1 only when the psi I is equal to psi j, that means I equals to j, and it will be a delta function provided this psi I and psi j, they are normalized. Okay. So, so that is shown here, and when an eigenfunction having a particular eigenvalue, say EI, okay, is expressed as a linear combination of a set of eigenfunctions, then we can write like this. Right. So what we mean here is that I can write the eigenfunction as a function as a linear combination of several eigenfunctions. So psi equals to say psi I, psi j, psi k, and so on. So there will be a coefficient like c I, c j, c k, and all these things. So that is given here, that this energy also can be expressed as a linear combination of a set of eigenfunctions. Now, in this particular equation, all the products where this j is not equals to j prime, they will vanish. Okay. So this will be the result provided j is not equals to j prime. Okay. Now, if each psi ij is normalized, then normalized with normalized to 1, then what we will have from here is this, right? This is the normalization. So this particular coefficient, if we take the square of and then sum it over all j values, then I will get a value of 1. So having this knowledge, now we can show that the eigenfunctions for any given molecule can act as the basis for the irreducible representation of the symmetry point group to which that molecule belongs to. Okay. This is a very, very important clause. Okay. So we are going to show that, but I can tell you at the beginning itself that yes, this eigenfunctions of any for a given molecule for any given operator will act as the basis of for the symmetry group to which the molecule belongs to. So now we are going to show that. If we take the wave function for the molecule and carry out the symmetry operations R, okay, so what we are going to have, so suppose I have some wave function psi I, and I operate each symmetry operations given by R. Okay, so R may be any symmetry operation. So whatever the resultant, I am operating my Hamiltonian operator on that. Now in that case, what I am going to have, because H and R they commute, so therefore H and R they are not going to interfere with each other's duties, right? So therefore when I operate Hamiltonian on this R psi I, it is going to give me the same eigenvalue EI and return me this R psi 1. Therefore, this R psi 1 also act as an eigenfunction of the Hamiltonian operator. That is obvious here. Now, this psi I, each psi I is normalized. So therefore, and we said that we are normalizing it to the value of 1. So now if we couple this to fact that when you operate any symmetry operation on this psi I, that R psi I is an eigenfunction, is also an eigenfunction of this Hamiltonian operator, for which psi I is a eigenfunction. And next is that each psi I is normalized. So that means in order to have R psi I as an eigenfunction, R psi I must be normalized. So it should be such that R psi I equals to plus minus psi I. Okay. So either it can be symmetric or antisymmetric. The eigenvalue will be either plus 1 or minus 1. So it simply means from symmetry point of view, that is this psi I is either symmetric or antisymmetric with respect to the symmetry operations. Okay. So now if we apply all the symmetry operations of the group okay, to onto an eigenfunction psi I, which belongs to a non-degenerate eigenvalue. Okay. So, what do you mean by non-degenerate? That when we operate Hamiltonian on the psi I, then the eigenvalue that is generated is non-degenerate. Okay. So then we can generate a representation of a group of the group as gamma I r. Okay. Now we have just seen that r psi I equals to plus minus psi I. That means the eigenvalue is plus minus 1. So therefore, the elements of this representation gamma I of any given symmetry operation will be equal to either plus 1 or minus 1. So the overall representation that I will get for the point group, taking this r psi 1 as my basis, or psi 1 as my basis, I will get the characters which are only unity, either plus 1 or minus 1. Therefore, this the dimension of the representation is 1. Therefore, it is not further reducible. So we are getting an irreducible representation, right? And that's what we said at the beginning, that the wave function of any given molecule can act as basis for the irreducible representation of the symmetry point group to which the molecule belongs to, and that's what is the proof here. Okay. So so in the following class, we will look at some more properties of the this wave functions of a molecule, and we will also try to correlate that how these wave functions get transformed into different irreducible representation and all, and we will then see how this can be actually applied onto the real problems. So we'll come back in the fourth day of this class tomorrow. So till then, thank you.